I want to figure out how long it takes for this charge to travel through the plates. Now, you don't have to rewrite the givens if you already have them written, but I will. What we're saying is that we have these two charged plates, one plate being positive, the other plate being negative, and we have this electron that's being emitted into these two charged plates with an initial velocity, and we're claiming that the initial velocity, we'll call it v1x, is 1.027 times 10 to the power of 8 meters per second. Yep.
Are both plates supposed to be positive?
Oh my gosh, one plate's supposed to be negative. Thank you. Oh, it must be the morning. Negative plate and a positive plate. Sorry. All right, well, forget about the fact that that's a positive and a negative, where the negative on the bottom is kind of messy now. Anyway, positive plate on the top, negative plate on the bottom. I'm not going to bother with the whiteout. I wish this was on a computer. I could just delete it. Undo. All right, 1.027 times 10 to the power of 8 meters per second is the initial x velocity. I want to know how long it travels between these two plates for. What other key piece of information that you've been given previously could I use here? Sherry? Yeah, the length. So delta dx was equal to 6.0 times 10 to the negative 2 meters. And Sherry, maybe you can help us. How could we find the time that it travels through the plates? Okay, so she says v equals delta d over delta t, where there's no acceleration in the horizontal direction, and that means that delta t would be equal to, what was it, Sherry?
The length divided by the velocity.
Yeah. Okay, delta d in the x direction divided by v in the x direction. Now we could just say v average in the x direction, because we know that v1x is equal to v2x in the x direction if there's no acceleration in the x direction. So let's just call it vx. Okay? So delta t, time to travel between these two plates, that is from the entrance point to the exit point, is going to be equal to 6.0 times 10 to the negative 2 meters divided by 1.027. Maybe somebody's going to beat me to it. How long does it take to get through this thing? What is it?
Not very long.
5.84 times 10 to the
Negative 10. The answer is, yeah, 5.84 times 10 to the power of negative 10 seconds, or according to Daniel, not very long. Okay, good. So really, really short period of time. This is a fast thing, traveling a small distance. So the fact that the numbers are so tiny, not really all that surprising. Okay, maybe we can use this page, try and reduce our waste a little bit to do another problem. So a part I. I for part B. Find the vertical deflection for the charge. In other words, how much does the charge get pushed upwards vertically before it exits the plates? Okay, so if it starts off at this height, how high is it when it comes out? Must be up, because we said that the acceleration is upwards, because the net force is upwards on this thing. Let's put the question in writing, though. What is the vertical deflection distance upon exit of the plates? Now this is really very much like a projectile problem. What am I really asking for if we were talking in projectile terms? Which variable am I looking for? Yeah, delta d in the y direction. Really, it's saying what's delta d in the y direction for this upside down projectile where gravity isn't the force but electrostatics are the force, right? That's a doable thing. So some information that we know in the y direction. Remember, time is always important no matter what direction you're going in. So time is something we're going to carry through from the previous question. I suppose I should have kept a better unrounded value, but 10 to the power of negative 10 seconds, we'll just get it out for process. What's another piece of information for the y direction? Yeah?
Acceleration in the y.
Okay, acceleration in the y. What was acceleration in the y? I don't recall.
1.758 times 10 to the 13
10.
meters per second.
Well, we're just looking for the magnitude. We know it's going to be accelerating upwards. Meters per second squared, and we could say up if we want to be specific about it. Is there any other information that we know about the y direction? What are our kinematics values that we usually want to know? We know displacement, or we want to find displacement. We know the time. We know acceleration. What's another key thing we could look for? Velocity. What's velocity in the y direction initially? Yeah, 0. That's nice to know. 0 meters per second. What's a nice kinematics formula? I mean, we don't even have to do a lot of derivation here. We could just go right back to grade 11. What's a nice kinematics formula we could use to find the vertical displacement for this thing as it exits the plates?
Delta D equals V1 delta T plus 1/2 A delta T.
I like it. Okay, delta D equals V1 delta T plus 1/2 A delta T squared, where all the V's and the D's and the A's are in the y direction. So we know that V1 is equal to 0, so that simplifies that nicely. V1 in the y direction is equal to 0. And I'm sure that people can write this quicker than me. I don't think that I can fit all these values in. I know that the A value is going to go in here, and I know that the T value is going to go in here. Just for the sake of sanity, can I ask you guys to calculate it, and I'll just write the final answer. Okay? And if you're the sick person following along at home, put it into your calculator and see if you get the right answer. Cece's not here today. She's sick. Yeah. 2.997 times 10 to the negative 6. Okay. 2.997 times 10 to the negative 6 meters. Or if we want to write it, well, we could write this in micrometers, right? It's already almost too convenient. We could say this is, 3.0 micrometers. Nice, eh? Yeah, it's like it's begging to be converted. Now, there's IV and there's V left to go. Are you ready for it? Can you handle it? Yeah.
Wait, can you go back?
Oh, sorry.